everyone, my name is Mr. Isaac Berry from New York University, and today, to celebrate the fact that I'll be starting dynamics, which is essentially a classical mechanics course, in a few days, actually I think 3 days, I'll be attempting to prove that the shortest path between 2 points is, well, I can't reveal it to you yet. So, if I have x1, if I have x1 comma y1.
You want to show the book you following?
Oh yes, of course. I haven't read the book that much, but I've heard some very good things about it. It's Classical Mechanics by Professor John Taylor, and we're starting from chapter 6 in our own course.
All physics students should buy this book.
Okay, so here we have a point x1 comma y1. And if you want to follow along, this is chapter 6.2, by the way. So, you have a point x1 comma y1, and then you have a point x2 comma y2 in totally Euclidean space. It could be R2 or R3, but we're just considering R2. So, in this scenario, right here, what is the shortest distance between these 2 points? What is the shortest path?
D is the square root of x2 minus x1.
I said, what's the shortest path? What path should you take between these two if you want to walk the lead?
A straight line.
Okay, good.
That straight line, isn't it? D is equal to square root of
That's
x.
the length of the straight line.
Okay.
So, of course, if you're being precise, the equation of this straight line is y is equal to the slope plus y2 minus the slope multiplied by x2. So, this is if you're being precise about the equation. But what we'll set out to prove today is using the calculus of variations, proving that this is the shortest path between 2 points in Euclidean space. So how do we go about doing that? First of all, let's say we don't know this. We're dumb. We don't know that the shortest path between 2 points is going to be a straight line. And so we make a guess. We say, maybe we can do this, turn around over here, make this awkward shape right here, and go all the way to point B. No, do you think this is the shortest path between these 2 points?
Absolutely not.
All right. So, let's see what went wrong here. So,
Everything.
okay. It looks like he doesn't like this path very much. So let's zoom in on one of the parts of this path. Now, if we take an infinitesimally small part, it can be approximated as a straight line. Now, this straight line has a length, dx, and a height, dy.
By the way, what are you proving?
We're proving that the shortest path between 2 points in Euclidean space is a straight line.
Oh, that's always true, except light doesn't take the shortest path.
It does, by the way. I said in Euclidean space.
Okay.
Do you know what Euclidean space is?
I think I do. So what space light doesn't take shortest path?
Light always takes the shortest path with regards to distance in a geodesic. Space-time is not flat most of the time, unless you're considering a totally empty universe. This is the kind of thing that light has to go around.
This is black hole. If you put a mass, it creates hole on the space.
Yes, we're proving this for Euclidean space, not for anything else.
Okay.
We're proving this for totally flat space. So we have dy and dx over here. And you can probably figure out that the slope here is just going to be dy dx. Looks familiar, right?
Yes.
So, the slope of this is dy dx. But what's the length? Well, it's obviously the square root of dx squared plus dy squared. Just the Pythagorean theorem. That's not where you're supposed to be looking. Well, please. So, the length of this segment right here is the square root of dx squared plus dy squared. But a nice thing we can do here is we can factor out dx squared. It's a very nice insight. And we can get, well, what's on the... and what is this? Well, it's just the derivative of y with respect to x. So, this is the length of our little line segment. And we're going to call it ds. So then, we're integrating from point 1 to point 2 over our path ds. So then, we expand that integral. And we get from the x-coordinate of 1 to the x-coordinate of 2, this right over here. And this is where you get to see the essence of what the calculus of variations is all about. It's about using the basic optimization that we know from calculus 1 and using that to minimize integrals. So that's the very big concept behind it. And so the whole thing follows from a very special equation called the Euler-Lagrange equation. And we'll be deriving that today in order to solve our problem. So I'm going to totally follow the book's derivation, if you didn't realize already. So, let's say that the book has an answer key for us. So we're trying to figure out the extremely hard problem of finding the shortest path between 2 points. And the book has an answer key for us. The book already knows that the shortest path is this. But we don't know what the shortest path is, but we know it has to be something. So, we let the equation for the shortest path be equal to y of x. So then, we try a totally bonkers solution. We try something like this. And we call this capital Y of x. And now, you look at the error that was caused. If you look at the error here, this is what we're going to call eta of x. Such that, I'll color code it, capital Y of x, our guess is equal to the correct solution, lowercase y of x, plus some constant alpha, which acts as a scaling factor for some arbitrary error, eta of x. So I'm totally following what the book says right now. So we obtain the correct curve by just setting alpha to 0. So I'm totally following this right here and seeing if I can understand it well enough to explain to you guys. So, how do we figure out what we have after all of these shenanigans? Well, when we take this integral, in general, from x1 to x2, it's going to be some function of this fake solution, the derivative of the fake solution, and, well, x. So that's a 3-variable function. Very scary, right? But what you come to realize is that, of course, each of these functions, the first one is y plus alpha eta. The second one is y prime plus alpha eta prime. Remember, eta is a function too. And the third one is just x. So you have to realize y is a function of x, eta is a function of x, y prime is a function of x, eta prime is a function of x. So this is a function of x, this is a function of x, this is x. This is really just a function of x at the end of the day. That's why our integrand, or our variable of integration, is just dx. So let me turn the page real quick. Okay, looks like we're following the solution pretty well so far. So, okay, so here now, what we're doing is we're optimizing, right? So let's take a look at the very classic optimization problem, where you're a farmer that lives right next to the sea, and you need to build a fence that encloses as much area as possible with limited fencing. So let's say you have 40 fences, and you want to enclose, and each fence is like 1 meter long, and you want to enclose the maximum area. Well, what do? You know that you have, this is the width, or this is the height, this is the width. So this is going to be equal to 2 height plus width right here. And what we're trying to optimize is the height multiplied by the width. So what we do here is we solve for the width as a function of height, and then plug that in right here, and then we have the single variable function, which we just find the minimum, or in this case, the maximum of. So we can find the maximum of this very simply. That's actually just the vertex, since we have a quadratic function right here. But that just gives 40 minus 4h is equal to 0. So h is equal to 10, and that means the width is equal to 20, which means that with something like this, you can enclose a total of 200 square meters at your maximum. So notice that we took a derivative over one single variable and then set that derivative to 0. That's very similar to what we're going to be doing here. So we...
How much longer, baby?
A lot longer.
Don't scare me. How long?
So...
okay, give me an estimate. I'm a little sleepy.
20 minutes?
Still?
So here's the thing.
Is there any break? No.
Well,
Okay. All right.
so here's the thing. We're solving for this single variable function of alpha. So we are naturally going to try and minimize that. So we are going to try and take ds d alpha. Only that's a little bit more complicated than you might think. You have to use the multivariable chain rule. So,
Oh, by the way, baby, did you order analysis 2 book?
no. I don't know what textbook he's using yet.
He did not post the syllabus?
Okay. So, here's what we know. This is going to be equal to, of course, partial f partial alpha dx. But then, what is partial f partial alpha? Well, we know f is a function of our incorrect solution, the derivative of our incorrect solution, and x, which expands to be the correct solution plus alpha multiplied by our error, comma, our correct solution prime, plus alpha multiplied by our error prime, comma, x divided by partial a. So, this is what we're looking at here. And now, how can we use the multivariable chain rule? Well, that's pretty weird. I don't like that. Oh, yeah, that works. So, you might recall that partial f of x of t, y of t, partial t is, well, equal to partial f partial x, I mean, what we plug back into this expression here. And since we're trying to minimize something, we want to set the derivative to 0 to look for extrema. Okay.
We want to give the credit to the author of the book.
Well, yeah, of course.
So, yeah.
John R.
No,
Taylor.
hold it. I didn't see it. Yeah. So, this is the best book for classical mechanics.
Okay, so back to what I was saying. To do this, what we are going to want to do is write this term via integration by parts. And well, how do we integration by parts it? That's an open question. Okay, so we are going to set this to dv and this to u apparently. So we integrate dv with respect to x. So that's of course just going to be eta. And then we're going to multiply that by u. And then what we have is minus our definite integral of, well, eta multiplied by d dx partial f partial y prime. Okay, this is slowly starting to take shape. Look at this in 6.7. Oh, okay.
What, you made some mistake?
No. What we know from before is that no matter how bad our path is, it still has to start at our initial point and end at our final point. Which means no matter how terrible we've made this, the error at the beginning has to be 0, and the error at the end has to be 0. As you can see from this graph right here. So, what does that mean for us? Well, that means that since we're bounding this from x1 to x2, this guy gets totally swamped. So we just get so we're going to move this to the other side of the equal sign to write now Oh, why do they use an additional negative sign? It is. Yeah, I'm not sure how they get, how they keep that negative sign. But anyway, we have eta prime multiplied by partial.
I'm gonna give you a pen so you can put it.
No, we're almost done.
Oh, okay.
Okay, and so now all we have to do, since these two integrals have the same bounds, is put this back over here again. Oh, and this would be eta, not eta prime. And we get partial f partial y. Well, eta on the outside, partial f partial y plus partial f partial y prime, or is it d dx partial f partial y prime? Oh, so do we keep the negative? Okay, this guy is giving. So he just rejects the negative sign out of nowhere. What the heck? Okay, change of plans.
The book could have made mistake.
It made a sign error. It just it shut up about it and gave us the correct answer anyway. So essentially, what's happening here is we take this, swap it to the other side, and flip the sign, of course, which means that when we, put it back. Well, I don't know why we put it to the other side to begin with. We didn't need to. At the end of the day, we just have 0 is equal to the integral from x1 to x2 of eta partial f partial y minus, well, d dx partial f partial y prime. So, this is doing pretty good here. And now, here's what we're going to say. This relation has to be true for every single possible eta we can think of. And so, the book makes a bold claim, this has to be 0. But how can we actually know that?
Baby! Can you move to whiteboard?
No.
I love whiteboard. No. Okay.
So, how do we actually know that this chunk right here is going to be equal to 0? Well, it says proof by contradiction. Assume that this is not equal to 0, but that this integral.
In physics, how many proofs are based on experiment and how many proofs are based on math?
This is not physics.
Oh, okay. God bless you.
Huh?
This is classical mechanics. How can it not be physics?
It's a mathematical tool that we use widely when it comes to classical mechanics.
I thought I'm the one
That's
who...
like saying algebra is physics because F is equal to m times A.
Daddy loves you, but I thought I'm the physicist here.
Okay, let me see. Okay, got it. So, let's say this is not equal to 0, right?
Yep.
So then, let's choose a very clever eta.
You did not answer my question. Okay.
So, let's say this huge function right here is equal to z of x at the end of the day. And z of x looks like, I don't know, this. Then it says, pick a very simple eta. Pick an eta that is equal to 1 whenever your function is positive, and then equal to negative 1 whenever your function is negative, then equal to 1 whenever your function is positive, and so on. that means that in the positive parts, it will have a positive integral. But in the negative parts, negative times negative means it will also have a positive integral. And in the positive parts, it's like we're taking the integral of the absolute value of g of x, which cannot be equal to 0 unless g of x is equal to 0 itself. What the heck?
Sorry, I cannot bring water for you. How long?
2-3 minutes.
Oh, okay. Because I'm holding 2 camera. And I have only 2 hands.
So there we go. We derived Euler-Lagrange equation. Now, let's plug it in for our special straight line
Can
case.
you do it on the whiteboard, please? No. Okay.
You're like a little kid.
Yeah, but I love whiteboard.
Alright, so here's what we're going to do. In our special case, we need to solve for this special guy right here in terms of the length L. So our function is just going to be the length L. And we use dx, I think we can still do that. And now, here's what we know.
Blackboard!
We already know from earlier that L is equal to the integral of the square root of 1 plus y prime squared dx. Yep, from x1 to x2. So, what are you pointing at?
Okay.
Is your attention span like a couple of seconds?
Yeah, loves you, baby.
Okay, so now we use a very funky thing called, I think, can we do that? Yeah, the fundamental theorem of calculus. Wait, can we do that? Oh yeah. Well, this is clearly not a function of y, as we can see here. It's only a function of y prime and x. So the derivative with respect to y is equal to 0. We should know that. But then what's the derivative with respect to y prime? Well, how does it know that? How does it know that? Well, what the book is telling me is that
Oh, by the way, why you are half of the book or 1/3 of the book?
because that's the chapter that we're supposed to start from. Everything before that is a basic review of Newtonian mechanics.
Oh.
We don't want to waste the entire semester learning things that we learned in the past 3 physics classes.
Okay, so first 100 pages or so are like reasons
We
physics?
need to, no.
Okay.
It's calculus-based physics.
Okay.
So up to 220 or so.
Okay.
Okay, so it's telling me that this should be equal to but how does it know that is what I need to know. Because that, I don't know, something about it tastes very, very bad to me. It's like the water has been poisoned. I don't know what I'm talking about. So I suppose this is what you get if you take. Sorry.
No, it's okay.
This is what you get when you take the. Oh. What it does here is it uses Fubini's theorem.
What? What theorem?
Fubini's theorem.
Fubini's
I know,
theorem.
he sounds kind of weird.
What country he's from?
Italy.
Oh, okay.
And it exchanges these two derivatives around. So it says this is basically equal to this. And what is dl dx? Well, we're integrating with respect to x, so naturally, taking the derivative, we'll just cancel that integral out. So we're only taking the partial derivative of this with respect to y prime, which is obviously just equal to, there's an extra factor of 1/2 that's going unaccounted for, so I'm going to write it in myself. Y prime over the square root of 1 plus y prime squared. And that has to be equal to 0. Is there 2? Yeah, I think so. Oh, no, the 2 is on the top. Oh no, but it's canceled out by the 1/2 from the power rule. So he's right. Okay. So that means that this is true, and so that implies that this is true, which implies that, oh, I did another mistake. I just realized that when integrating, you're generally supposed to put an integration constant at the end here. So this could be any number right here. It could be c, for example. So when I square both sides, this becomes c squared. So then I get y prime squared is equal to c squared times 1 plus y prime squared. So you get y prime squared is equal to c squared plus c squared y prime squared. So you get y prime squared times 1 minus c squared is equal to c squared. So you get this, which is a constant. And so that implies that the actual derivative
Is this the final line?
is a constant. And we're almost done.
Can you write it on the blackboard?
When you take the integral with respect to x, this just gives you,
Yeah, baby, write it on the blackboard.
which shows that the shortest path has to be straight.
Can you write it on the blackboard? Baby, baby, baby. Okay, all right, that's it.